Isang mapagpalang araw sa inyong lahat. For today, I will be discussing about the vibration analysis and control. This presentation was prepared by me and my other members. We are the group 6. In this chapter, we have 7 topics to be discussed. Sana po makinig kayo at may matutunan. Introduction. There are numerous sources of vibration, especially in an industrial environment, like impact processes, such as pile driving and blasting. Yung pile driving, ito yung gumagamit sila ng machineries or equipment na naghuhukay sa lupa at nagbabaon ng mga poste na ginagamit yon para sa pundasyon ng mga building or ng mga ginagawang tulay. Blasting, ito naman ginagamit sa mga minahan or sa mga quarry na gumagamit sila ng explosive devices upang mapasabog o mapaliit nila yung mga malaking bato. Also, vibration can be found on rotating or reciprocating machineries, such as engines, compressors, motors. Also, in transportation vehicles, such as trucks or yung mga pagsakay natin sa buses, sa trains, and aircraft. And also, vibration can be found on flow fluids. Kaya napakaraming pinanggagalingan talaga ng vibration. The presence of vibration often leads to excessive wear of bearings, also in wearing of the other components, na pwedeng mag-form ng cracks, na pwedeng mag-loosening ng mga fasteners, ng mga bolts natin, ng screws, and vibration can also cause structural and mechanical failures. Isa pa sa mga nagiging epekto ng vibration ay yung electronic malfunctions through fracture of solder joints and abrasion of insulation around electric conductors na sa sobrang vibration pwedeng mabalatan yung mga wire na pwedeng maging cause ng short circuit ng isang system. The occupational exposure of humans to vibration leads to pain, discomfort, and reduced efficiency. Vibration can sometimes be eliminated on the basis of theoretical analysis only. However, the manufacturing costs involved in eliminating the vibration may be too high. So, marami talagang expenses kung may plano kayong paliitin or i-eliminate totally yung vibration. Kaya, the designer must compromise between an acceptable amount of vibration and a reasonable manufacturing cost. Vibration analysis and control is the design or modification of a system to suppress unwanted vibrations and to reduce force or motion transmission. Ayun nga. So ito yung pagdi-design or pagmamodifika ng system upang mabawasan or ma-dissipate yung mga vibrations and mabawasan yung mga outside or external forces and motion transmission. To mitigate the impact of vibration, we design and analyze the parameters, including the inertia properties, stiffness properties, damping properties, and even the system configuration, including the number of degrees of freedom. So, in this chapter, we shall consider various techniques of vibration control. Vibration nomograph and vibration criteria. So, when we say nomograph, it is the diagram representing the relations between 3 or more variable quantities by means of a number of scales. So, vibration nomograph, it displays the variation of displacement, velocity, and acceleration amplitudes with respect to the frequency of the vibration. So, here we have the harmonic motion, the equation 1, and the velocity equation 2, the formula for acceleration, equation 3, and the equation for the amplitude of velocity, the Vmax is equals to 2 pi times frequency times the amplitude. And the equation for the amplitude of acceleration, Amax is equals to negative 2 pi times frequency times Vmax. Taking the logarithm of equation 4 and equation 5 by the use of quotient rule and product rule, we can obtain the equation 6 and equation 7. From that, when x is constant daw, the lone Vmax varies linearly within the lone 2 pi f. Same lang sa amplitude of acceleration daw. Kapag constant siya, the lone Vmax mo still varies linearly with lone 2 pi f. This is shown as a nomograph in the next slide. Sa next slide natin, may kita yan. And thus, every point on the nomograph denotes a specific sinusoidal vibration. So, this is our vibration nomograph. As you can see here, in the x-axis in the horizontal line, it represents the frequency line in hertz, and the y-axis in the vertical axis na to, it represents the velocity line in millimeter per seconds. The diagonal line, downward from left to right, it represents the acceleration line in meter per second squared. And the diagonal line, the upward from left to right, represents the displacement line in micrometer. So, the vibration nomograph is para lang siyang Cartesian coordinate plane. Kasi dito, ipa-plot mo lang yung mga nakuha mong parameters. Tapos, malaman mo dito, dahil may mga naka-indicate naman dito na velocity, frequency, acceleration, malaman mo dito kung acceptable pa ba or unacceptable na yung mga values ng vibration. Kung makasira na ba ito sa machine mo o hindi pa. Ito, according to ISO, or the International Organization for Standardization 2372, vibration severity of machinery is defined in terms of the root mean square or RMS, value of vibration velocity. So, pag binalikan natin yun, dito sa right side, sa ISO 2372, yung machine vibration sensitivity, dito nyo makikita yung quantity niya, yung 0.11 mm per seconds to 71 mm per seconds. As you can see here, the 0.11 mm per seconds, sinasabi na good pa siya. But in 71 mm per seconds, kapag umabot na dyan yung velocity mo, it's said to impermissible or unacceptable na siya. Nakasira na siya ng machine mo. While on the ISO DP 4866, dito sa left side sa upper, it gives the vibration severity for whole building vibration under blasting and steady state vibration in the frequency range 1 to 100 Hz. So dito, kung makita nyo, yung 3 to 5 millimeters per seconds dito is threshold damage. Pag sinabi natin threshold, ito yung the level at which you start to experience something. Kaya may nararamdaman ka na. Nung paglongpas ka pa doon, itong 5 mm to 30 mm per seconds, magkakaroon tayo ng minor damage. And kapag beyond that, magkakaroon tayo ng structural damage like destructive wall damage, cracks, etc. Lastly, the ISO 2631 or it is said the human sensitivity. Dito, makikita natin kung ilang frequency lang yung kayang i-absorb ng katawan ng tao natin. So, mas makikita natin dito yan sa next slide. So here, vibration frequency of sensitivity of different parts of the human body. Makikita natin dito kung ilang hertz lang yung kayang i-absorb ng katawan natin. Like in the head, 25 hertz, the eyeballs, 30 to 60 hertz. As you can see here, the hand has the highest frequency because it has 50 to 150 hertz yung kaya niyang range na ma-absorb. Dahil yung kamay natin yung mahawak lagi ng tools, syempre mga martilyo, mga jackhammer, and pelvic mass or buttocks natin yung may pinakababa. 4 to 8 hertz siya. Beyond that, pwede na madamage or magkaroon tayo ng paramdam na discomfort. So we have sample problem here, helicopter seat vibration reduction. So the seat of helicopter with the pilot weighs 1,000 Newton and it is found to have a static deflection of 10 mm under self-weight. The vibration of the rotor is transmitted to the base of the seat as harmonic motion with frequency 4 Hz and amplitude of 0.2 mm. So we need to determine what is the level of vibration felt by the pilot and how can the seat be redesigned to reduce the effect of vibration. So first, for the computation of the level of vibration felt by the pilot, we list the given. We have the mass, static deflection, frequency, amplitude of base displacement, and we compute for the stiffness using this formula, and we get 10 raised to 5 Newton meter. And for the natural frequency, we use this formula, the excitation frequency divided by 2 pi. So we get this, the square root of k, or stiffness, divided by m, divided by 2 pi. So substitute, then manipulation of units, we obtain the 4.9849 cycle per second, or hertz. And for the frequency ratio, we just divide the excitation frequency over the natural frequency, and we get 1.2462. So for the amplitude felt by the pilot, we use this formula, and we can obtain the 0.3616 millimeter. And for the amplitude of velocity, we use the formula I tackled a while ago. We can obtain the 9.088 millimeter per second. And for the amplitude of acceleration, we use the formula, the 2 pi f squared times most amplitude. So we get the 0.2284 meter per second squared. So for this, at 4 hertz daw, the amplitude of motion of 0.3616 millimeter may not cause much discomfort. However, the velocity and acceleration levels at 4 hertz are not acceptable for a comfortable ride. So hindi siya comfortable. So, i-redesign natin siya para mabawasan yung vibration. In order to do that, try to bring down the Emax to 0.01 meter per second squared from 0.2284 meters per second squared. Ito nga yung kanina sa vibration graph natin. Kasi mas acceptable yung 0.01. So from that, we compute for the new amplitude. We get the 0.01583 millimeter. Then get the frequency ratio. So we solve the 3.6924. And for that, we can now solve for the new frequency of the seat using this formula. Then we solve for the 6.8066 rad per second. For that, we can solve for the stiffness. K is equals to natural frequency squared times mass. Then we can obtain the 4,772.71 Newton per meter. So therefore, this implies that the stiffness of the seat needs to be reduced from 10 raised to 5 Newton meter to 4,000. Diba? Ang laki ng pagitan nila. To be acceptable for a comfortable ride by using a softer material or by using a different spring design. Reduction of vibration at the source. The first thing you need to do to control vibration is to try to alter the source so that it produces less vibration. So, syempre, sa unang-una, kailangan mo malaman yung source ng vibration. Kung saan siya nanggagaling, kung saan nag-umpisa. In order for you to fix it or to alter it. Some examples of the sources of vibration that cannot be altered are the earthquake excitation, atmospheric turbulence, road roughness, and engine combustion instability. So, ayun yung mga sources ng vibration na hindi mo kaya ma-alter dahil it's either ito'y unexpected na galing sa Mother Nature or yung mga bagay na hindi mo control like the engine combustion instability. On the other hand, certain sources such as unbalanced in rotating or reciprocating machines can be altered to reduce the vibrations. And this can be achieved usually by using either internal balancing or an increase in the precision of machine elements. The use of close tolerances and better surface finish for machine parts which have the relative motion with respect to one another. Whirling of rotating shafts. What is whirling? Whirling is defined as the rotation of the plane made by the line of centers of the bearings in the bent shafts. In many applications, a heavy rotor is mounted on a light, flexible shaft supported in bearings. Unbalances and other effects will cause a shaft to bend at a certain speed known as whirling speeds. There will be unbalance in all rotors due to the manufacturing errors. So, these unbalances as well as other effects such as the stiffness, yung damping of the shaft, gyroscopic effect, and even fluid friction in bearings will cause a shaft to bend in a complicated manner at certain rotational speeds known as whirling. According to S. Graham Kelly, whirling is a phenomenon that occurs when the center of mass of rotor attached to a rotating shaft is not aligned with the axis of the shaft. So, yung whirling nga daw is yung kapag hindi pantay yung mass of the center ng rotor mo na hindi naka-align sa axis of the shaft. Because of that, the motion of the shaft and the eccentricity of the rotor cause an unbalanced inertia force in the rotor, pulling the shaft away from its center line and causing it to bow. Kaya nagkakaroon ng baluktot ang rotating shaft dahil nga sa unbalances ng inertia force at ng rotor. So, parang ganito. May pagkabaligo na siya. In this figure, consider a shaft supported by two bearings and carrying a rotor or disc of mass. Ito, meron tayong bearing dito sa magkabilaan at may rotor tayo sa gitna. In this figure, forces acting on rotor, inertia forces, because the acceleration of the mass center, spring force due to the elasticity of the shaft, and the external and internal damping forces. So, equation of motion. So, we have here a figure of a rotor with eccentricity. So, as you can see here, we have a y and x axis, and let O be the equilibrium position of the shaft when balanced perfectly. So, ito yung equilibrium position natin kapag nakabalance talaga yung shaft. And in this, the line OC here, the line OC or the line A dito, ito yung ito yung distance or yung rotor deflects radially by distance OC. So ito yung ganito kalayo yung yung distansya ng pag-deflect ng rotor kapag nagkakaroon ng whirling. And the line CG is assumed to rotate with a constant angular velocity. Ayun yung line CG. And we have here the A, that stands for eccentricity, the G, the center of the gravity, mass center of rotor yan, C, geometric center of rotor, and R, the whirl amplitude. From this figure, we can formulate or solve the equation of motion. Angular velocity of line OC and the theta is equal to d theta with respect to d time is known as the whirling speed. And it is general not equal to the rotational speed of the shaft. The equation of motion of rotor can be written as, so ito, yung equation natin ng inertia force or Fi is equals to elastic force, Fe, plus internal damping force, FDI, plus external damping force, FDE, and also we can write the formula of inertia force by Fi is equals to mass times R, which is the radius vector. And in equation 2, we have the value for the R, the formula for the radius vector. And for the equation 3, we have the elastic force or the inertia force rather is equals to mass times the value of R here. So in equation 4, it is the elastic force formula, which is the minus K multiplied by the X times I plus Y times J, where the K is the stiffness of the shaft. And in equation 5, it is the internal damping force, and where the CI is the internal rotary damping coefficient, and in the equation 6, it is the external damping force, where C is the external damping coefficient. So if we substitute the value of the inertia force, the elastic force, the internal damping force, and the external damping force into equation 1, we can obtain the equation 7 and equation 8. These equations of motion, which describe the lateral vibration of the rotor, are coupled and are dependent on the speed of the steady state rotation of the shaft. By defining the complex quantity of W as the W equals to X plus Y times I times Y, and where I is equal to negative 1 raised to the power of 1 half. If we get the sum of the equation 7 and 8 and multiply it by I, we can obtain the single equation, the equation 9, speeds. A critical speed is said to exist when the frequency of the rotation of the shaft equals one of the natural frequencies of the shaft. So kapag mag-equal ang frequency of the shaft and mag-equal siya sa natural frequency of the shaft, magkakaroon tayo ng critical speed. So, the undamped natural frequency of the rotor system can be obtained by solving equation 7, 8, or 9, retaining only the homogeneous part with the CI or the internal damping coefficient is equal to external damping coefficient to equal to 0. So, this gives the natural frequency of the system, the critical speed of undamped system. So, kung makikita nyo dito, yung formula ng critical speed natin ay same lang ng natural frequency. Then when the rotational speed is equal to critical speed, the rotor undergoes large deflection, and the force transmitted to the bearings can cause bearing failures. Ayun nga. Kapag mag-equal yung rotational speed at yung critical speed mo, magkakaroon tayo ng resonance or magkakaroon ng large deflection. Kaya pwede siyang mag-cause ng failures ng mga components natin, lalo sa bearing. And a rapid transition of the rotating shaft through a critical speed is expected to limit the wheel amplitude. On the other hand, if the slow transition of the rotating shaft through a critical speed is expected to aid or to help to be bigger the wheel amplitude. Kaya kapag mas mabilis yung ikot, yung amplitude mo hindi ganoon kalaki. Hindi gaya kapag mabagal yung ikot, yung transition mo, mas lumalaki yung amplitude na mas nagiging dahilan upang magkaroon ng failure yung system mo or yung component. Response of the system. To determine the response of the rotor, we assume that excitation to be a harmonic force due to the unbalance of the rotor. So to get the equation of the response of the system, we solve the equation 9 and find the rotor's dynamic whirl amplitude resulting from the mass unbalance. So we assume that the CI or the internal damping coefficient is 0. And then substitute the 0 in the equation 9. So the equation reduces to equation 11. And equation 11 can be expressed as equation 12. And wherein kung makikita nyo dito, in the first term, it says it is the transient, and the second term it is said to be the steady state whirl. From this equation or the formula, where C, beta, and A and the phi are constant. Note that the first term on the left side contains the decaying exponential term. Ay nga yung sa may transient, representing a transient solution. While the second term of this equation denotes a steady state circular motion, or as what we call whirl. By substituting the steady state part of equation 12 into equation 11, we can find the amplitude of the circular motion whirl as ito nga yung equation 13. Kung makita nyo dito, yung A na to stands for the whirl amplitude. Tapos yung A na maliit stands for the eccentricity, and the R, the frequency ratio, and the zeta symbol is the damping ratio. Also, the phase angle, the phi times the arc is equals to arctan times the quantity of 2 times the damping ratio times the frequency ratio divided by 1 minus the frequency ratio squared, or the equation 14. By differentiating the equation with respect to the rotational speed of the shaft, and the result is 0, we can get the rotational speed at which the whirl amplitude becomes maximum. So we get the equation 15. So we have here the sample problem number 2, the whirl amplitude of a shaft carrying an unbalanced rotor. So, umpisa na natin. A shaft carrying a rotor of mass 50 kg and eccentricity of 2 mm rotates at 1,200 rpm. Determine the steady state whirl amplitude, and B, the maximum whirl amplitude during startup condition of the system. Assume that the stiffness of the shaft as the 40 meganewton per meter and the external damping ratio is zero point 0.1. So first, we need to list the given. We have the mass, the eccentricity, the 2 mm, the speed, 1 to rpm, stiffness, and the damping ratio. So to compute for the steady state whirl amplitude, first we need to compute the forcing frequency or the rotational speed of the shaft by using the formula 2 pi n divided 60. We get the 1,256.637 rad per seconds. And to solve for the natural frequency, as usual, we use the formula of the natural frequency. And we obtain 894.427 rad per seconds. And for the frequency ratio, we only divide the rotational speed and the natural frequency. And we obtain the 1.40496. So for now for the steady state whirl amplitude, we need to use the formula that I've been discussing a while ago. So substitute the value of the eccentricity, the frequency ratio, and damping ratio. So from that, we get the 3.895 millimeter for the whirl amplitude. So ngayon naman, we solve for the amplitude during startup condition. The W or the rotational speed of the rotor passes through the natural frequency. Using the frequency ratio of 1, we obtain the whirl amplitude by using this formula, eccentricity divided by 2 times damping ratio. So we get the 0.01 meter or 10 millimeter. Control of vibration. In many practical situations, it is possible to reduce but not eliminate totally the dynamic forces that causes vibrations. Several methods can be used to control vibrations. So ito yung mga methods para makontrol natin yung vibration. First, controlling the natural frequencies of the system and avoiding resonance. As we all know, resonance, if when the frequency of the excitation coincides with the natural frequency of the system, the response will be very large and it will be called the resonance. This condition is need to be avoided to prevent the failure of the system. Pangalawa, by using a damping or energy dissipating mechanism, we can prevent the excessive response of the system, even at resonance. And one of the methods to control vibration is to reduce the transmission of the excitation forces from one part of the machine to another by the use of vibration isolators or isolations. Last, by reducing the response of the system by the addition of an auxiliary mass neutralizer or vibration absorber na matatakal natin maya-maya. Vibration isolation. What is vibration isolation? It is the procedure by which the undesirable effects of vibration are reduced, basically by insertion of resilient member or the isolator between the vibrating mass and the source of vibration so that a reduction in the dynamic response of the system is achieved under specified conditions of vibration excitation. Isolation system is said to be active or passive. So we have two types, the passive isolator and the active isolator. The passive isolator, it consists of a resilient member or the stiffness and the energy dissipator or yung damping. Example ng passive isolator is yung metal springs, cork, yung mga nasa wine, nasa suka, felt, yung mga malambot na basahan galing sa balat ng hayop din, pneumatic springs, and elastomer rubber springs. While the active isolator, it is the comprised of servo mechanism with a sensor and signal processor and actuator. Medyo ano na to, medyo mas advanced siya kaysa sa passive. Vibratory forces generated by machines and other causes are often unavoidable. However, their effects on a dynamical system can be minimized by proper isolator design. So, by proper isolator design, ma-minimize natin mga yung mga unwanted vibration. So, as you can see here pala sa yung mga picture dito, these are good example of passive isolators. Yun na nga. An isolation system aims either to protect a delicate object from excessive vibratory forces transmitted to its supporting structure, or to prevent vibration generated by machines from being transmitted to its surroundings. The very goal or the very aim of isolation system is that the natural frequency of the supported system must be small compared to the disturbing frequency in order for avoid the resonance or the excessive vibration. And it can be done by using soft spring. We have here the figure 3.6.1. It is the disturbing force transmitted through the springs and damper. The other problems of reducing the force transmitted by the machine to the supporting structure has the same requirement. The force to be isolated is transmitted through the spring and damper. As shown in figure 3.6.1, its equation is the transmitted force is equals to the stiffness or K times to amplitude multiplied by the square root of 1 plus the quantity of 2 times the damping ratio and times by the disturbing frequency over the natural frequency squared. So this is the equation number 1. The disturbing force is equal to the disturbing force times sine times to the disturbing frequency times the time. And so the equation 2 is the equation for the amplitude, and the TR or the transmissibility is the ratio that transmitted force to the disturbing force. So yung TR natin, ito ay unitless kasi ratio lang siya. Siya ay ratio lang ng FT over FO. That is our equation 3. And when damping is negligible or zero, the TR reduces to 1 over the quantity of disturbing frequency over the natural frequency squared minus 1. So ito yung ating equation number 4. And the equation of TR can also express as the equation number 5, wherein it has the statical deflection and acceleration of gravity. To decrease the amplitude of the isolated mass without changing the TR, the smaller mass is often mounted on a large mass. Stiffness must then be increased to keep the ratio K over M plus M constant. Isolation of source of vibration from surroundings. So here we have TR is equals to 1 over frequency ratio squared minus 1. In here, the frequency ratio is always greater than by by the square root of 2. And in vibration isolation, dapat laging mababa ang damping ratio para mas maganda yung sistema. And by defining the frequency ratio is equals to the disturbing frequency divided by natural frequency. So we have the 2 pi n over 60 multiply mo sa reciprocal ng formula ng natural frequency. Then we have that square root of 2 minus r over 1 minus r, where the r is equals to 1 minus tr. So substitute the values and manipulate the units and manipulates the formula, and we get the 29.9092 multiplied by the square root of 2 minus r over the statical deflection multiply the quantity of 1 minus r. So ito yung magiging formula natin. So we have here the sample problem number 3. A machine of 100 kg mass is supported on springs of total stiffness of 700 Newton meter and has an unbalanced rotating element, which results in a disturbing force of 350 Newton at a speed of 3000 rpm. Assuming a damping factor of 0.20, determine its amplitude motion due to the unbalance and the transmissibility and huli yung the transmitted force. So uh, first we need to list the given. We have here the mass, the stiffness, the disturbing force which is the 350 Newton, the speed, or the 3000 RPM, and the damping ratio, which is the 0.20. First, we compute for the statical deflection of system. So we need to use the formula of mass times the gravity acceleration and divided by the stiffness. So by and substitute the the values and cancel that the units that needed to be cancelled. So we get the 1.4014 millimeter. For the natural frequency, we use the formula of it, then substitute the values, then compute. So we get the 13.32 cycle per seconds or hertz. So for computation of the amplitude of motion, we use we use the we use the equation number two from I discussed a while ago. We use the formula of the equation number two and substitute the values and cancel the units. Then we have the amplitude of 0.0379 millimeter. And for the TR is equals to the transmitted force divided by the disturbing force, or the TR can also written in this formula by the square root of 1 plus the quantity of 2 times the damping ratio times the disturbing frequency divided by the natural frequency squared divided by or all over the 1 minus the quantity of disturbing frequency divided by natural frequency squared to the power of 2 plus the quantity of 2 times the damping ratio times the frequency all of divided by the natural frequency squared. So substitute the values and cancel that the unit that needed to be cancelled, and we get that transmissibility of 0.1369 and it is unitless. And sa huli, for the solve and for the computation for the transmitted force, we use the formula above or here or the Ft over Fo. So manipulate the units or the formula. So we have that 350 Newton times 0.1369. So we obtain that transmitted force of 47.9 Newton. Vibration absorbers, or also called as dynamic vibration absorbers. It is a mechanical device used to reduce or eliminate unwanted vibration. It consists of another mass and stiffness attached to the main mass that needs to be protected from vibration. The vibration absorber is commonly used in machinery that operates at constant speed because the vibration absorber is tuned to one particular frequency and it is effective only over a narrow band of frequencies. The common application of the vibration absorber is on the reciprocal tools like the sanders, saws, and compactors, and large reciprocating internal combustion engine, which run at constant speed for minimum fuel consumption. Also, the vibration absorbers also used on high voltage transmission line to mitigate the fatigue effects of wind-induced vibration. So, uh, when the excitation frequency coincides with the natural frequency, the system may experience excessive vibration or yung resonance nga. In such cases, the vibration of machine can be reduced by using vibration neutralizer or yung vibration absorber, simply another spring mass system. The dynamic vibration absorber designed such that natural frequencies of the resulting system are away from the excitation frequency. So here we have a figure, the undamped dynamic vibration absorber. And when we attach an auxiliary mass M2 to a machine of mass M1 through a spring of stiffness K2, the resulting 2 degree of freedom system will be look like this figure. So from this, we have the equation 1 and equation number 2. By assuming the harmonic solution, we have the x sub j with respect to time is equals to x sub j, the amplitude sub j, times mo sa sine and multiply to the frequency multiplied by time, and wherein the j is equals to 1, 2. From this, we can obtain the steady state amplitude of the masses M1 and M2. So we have the equation number 3 for the amplitude of 1, and the amplitude of 2, we have the equation number 4. We are primarily interested in reducing the amplitude of the machine, the x sub 1. In order to make the amplitude of M1 to 0, then the numerator of equation should be set equal to 0. So we have the, the disturbing frequency squared is equals to the stiffness 2 divided by the mass 2, and the disturbing frequency squared is congruent to the disturbing frequency sub 1 squared is equals to the stiffness 1 divided by the mass 1. From that equation 4, we can obtain the the x1 or the amplitude 1 and the amplitude 2, the equation 5 and equation 6. So we have the last sample problem here. A diesel engine weighing 3,000 Newton is supported on a pedestal mount. It has been observed that the engine induces vibration into the surrounding area through its pedestal at an operating speed of 6,000 rpm. Determine the parameters of the vibration absorber that will reduce the vibration when mounted on the pedestal. The magnitude of the exciting force is 250 Newton, and the amplitude of motion of the auxiliary mass is to be limited to 2 mm. So we solve it. We have frequency of 6,000. Divide it by 60, you get 100 RPS or 100 Hertz. So alam naman natin na in 1 Hertz, meron tayong 6.28 rad per seconds. Convert it and we will have the frequency of 628.32 rad per seconds. Then, given here, we have the 250 Newton for the exciting force and the amplitude of 2 millimeter and the weight of the engine, that 3,000 Newton. Since the motion of the pedestal is to be made equal to 0, the amplitude of motion of the auxiliary mass should be equal and opposite to that of the exciting force. So, by using the formula of exciting force, F sub O is equals to second mass multiplied by the frequency or the disturbing frequency squared multiplied by amplitude 2. Then we substitute the values, then we calculate it, and we can calculate the second mass that is equal to 0.31665 kilogram. Also, we need to calculate the spring stiffness or the second spring stiffness. So from the formula of the natural frequency, we manipulate the units or the formula, and we have the formula of K is equals to disturbing frequency squared times mass. So here we have the 628.32 squared multiplied by the mass, or the 0.03166 kilogram. So we obtain the 125,000 Newton meter of stiffness. So ayun lamang po. Maraming salamat sa pakikinig po. God bless.